Okay, all right. So we'll get started here, and today's lecture is on describing data. So we'll start there. Just a few administrative things. I have a CampusWire discussion forum set up. You can join here. Here's the join code. You should have also received an invitation, and it's just a place where you can ask questions and answer each other's questions. The TAs and I will also be there to help answer questions with whether it be concepts from the class or other things. Okay. Other important thing, don't forget to do the viewing quizzes. Okay, so there's a viewing quiz that corresponds to each lecture, and the quizzes are due for Monday's lecture. They're due Tuesday nights at 11:59, and then for the Wednesday lectures, so today's lecture, the viewing quiz is due Friday at 11:59. Okay, the viewing quizzes are worth 18% of your grade total. And there's a total of 10 quizzes and one is dropped, which means each quiz is worth 2% of your total grade. And just for some perspective, your lab assignments are worth 2% of your total grade as well. So so I'm weighing these quizzes just as heavily as each lab assignment, and because I think it's important that you just show up and attend lecture. Okay. Sometimes I browse the UCLA Reddit and UCLA subreddit, and I saw this post from, I guess, finals week of spring quarter, and this person wrote, they have a final at 11 and they haven't watched any of the lectures since the midterm. You don't want to be doing this to yourself. Okay, marathoning lectures is absolute misery. There's no way to enjoy such an experience. It can be a subject you love, but just the idea of marathoning is it sucks your soul and life. So don't do that. The purpose of the viewing quizzes and the reason why they're only open for a short window of time is to kind of push you so you stay on track. And that's it. Okay. Yeah. Don't do that. Okay. All right. There's also the Gradescope quiz. The practice one is up. That's quiz 0. That's due tonight at 11:59 p.m. The file needs to be uploaded by the deadline. So it's not that you open the quiz by 11:59, but the quiz itself needs to be completed by 11:59. Okay. This quiz 0, its purpose is to get you familiar with the Gradescope process, so that when you do an actual quiz, which is due Friday, that you won't run into any issues. Okay, because there's, the quiz is already stressful. You get there's a 1 hour time limit on the quiz, so just the fact that a time limit exists makes it a slightly stressful experience. And so you don't want to be fumbling around with trying to figure out how to upload your file, how to get your file from your phone to your computer. No, these are some things that you want to practice ahead of time. So anyway, that's quiz 0, and it's worth 1 point of extra credit. So yeah, Gradescope quiz it's not graded, okay? But if you complete it, you'll get a point of extra credit. All right. So that's it. Okay. Yeah, I think one of the questions is like, take the mean of 5 numbers or 6 numbers, and I'm looking at the submissions, and a bunch of students couldn't even be bothered to take the mean of 6 numbers. So I was a little bit surprised by that, but whatever, it's not being graded. So okay. If it's been a long time since you've taken a math class, it could be helpful to review some of the basics of algebra. You don't need a whole lot of math background, but you definitely do need it, right? So you need to be comfortable solving equations and inequalities, which involves, working with decimals and fractions and proportions and things like that. You also need to need to be comfortable with linear equations and graphs. So, so these are important. I know everybody in the, Stats 10, it's a very, very diverse class as far as majors and backgrounds and things like that. So for some of you, it might be like 5 years, more than that, since you've taken a math class and you haven't had to do any kind of numeric work in your college experience, and that's totally fine. But I don't want that to become a hindrance in just making progress in the class. All right, any questions before we get started? Okay, and again, you have your participants panel, and you can use your icons to either raise your hand, say yes, say no, give me a thumbs up, thumbs down, and those things show up, and I can use those to just kind of gauge how things are doing. It's very different. You know, when I'm teaching in person, I'm able to kind of just look out at the classroom and kind of gauge just based on students' facial expressions how they're doing. I lose a little bit of that. You know, some of you guys have your webcams turned on, so I appreciate that, and that's always helpful. But it's hard to tell if someone's fully engaged on their computer or not. It's a lot harder to tell than when you're lecturing in person. So anyway, your feedback icons are very helpful. And then of course there's the chat for you to ask questions. All right, let's get started with today's lecture. And the big picture goal for today's lecture is describing a distribution of values, okay? And this is important because we need to be able to describe our data set if we want to be able to draw any kind of conclusions from it in the first place, right? So the big picture idea of statistics is that we can draw conclusions from the data, but even just the idea of drawing conclusions from the data requires that we have a way to be able to describe the data, and we use distributions to accomplish that, right? So our data, we can think of this as kind of a collection of values, a collection of numbers or observations or whatever we've gathered. And we often organize the values themselves into what's called a distribution. The distribution is a representation to show what values appear frequently, what values appear infrequently. Okay, we can represent distributions with tables or graphics, and we can describe those distributions using numeric summaries and the like. And the idea of using a distribution for this purpose is that we don't have to try to list off or mention every single individual in the data. Instead, we describe the entire distribution as one entity. And this allows us to then kind of describe one data set versus another data set without having to get into the details of every single individual that appears in each data set. So, you know, if somebody asks, how would you compare UCLA to, say, UC San Diego or something like that? How would you compare the student body of UCLA versus the student body of UC San Diego? You would have to find a way to kind of describe the entire populations as a whole or entire data sets as a whole rather than mentioning each individual, right? There's too many individuals in either situation. All right, and we can do this using visual diagrams and numeric summaries. So chapter 2 is all about the visual diagrams, and there's basically two key things. We're gonna look at histograms, which are for numeric data. We're gonna spend the bulk of chapter 2's time on histograms, and then we'll look at bar charts for categorical data, which is fairly simple. All right, let me give you the first quiz answer. All right, so the first quiz answer for today, week 1, Wednesday, first quiz answer is the letter B. The letter B as in boy. That is the first quiz answer once again. That is B as in boy for the first quiz answer. All right. Let's look at just some data here, okay? So this comes from the textbook. We're looking at the number of goals scored by some first-year college athletes. This is NCAA female soccer players in Division III. And this is how many goals they scored in the 2012 season. And so to interact with this data, what we can do is we can create a vector in R using the function C. And I apologize, this got cut off here. I should have it spill over onto another line. But you know, you'll do something like this in your lab where you use C and then you enter C parentheses and then you enter a bunch of numbers separated by commas. You assign it or you save that vector into some object and you give it that object a name. And so here we're going to give this object the name goals, and this is going to be a vector of all of these values. Okay, so a vector is kind of like a list. The list actually has a separate meaning in R, so you know we want to make sure we call this a vector, but it's a whole bunch of numbers kind of grouped together here. Okay. And the first way we can represent a distribution is using what's called a frequency distribution, okay? And in R, you can use this by calling tally, okay? You have to load the library Mosaic first, okay? So you call library and then you give it the name Mosaic, and that loads up a bunch of functions. And we will call tally onto the vector goals here. All right. Sorry, give me a second. Okay, sorry, I just noticed one of my settings was a little bit off and I had to fix that. Okay, so we call tally on the vector, and it creates a frequency distribution here, okay? So here it says 9 shows up one time, so there's one student who scored 9 goals, and then 11 shows up 4 times, okay? So there were 4 students who scored 11 goals, and we can see that because in our data set we have 9 once, and we have 11, 11, 11, 11, okay? So we have 11 does show up 4 times, 12 shows up 1 time, and then 13 shows up 5 times. And that's exactly what we have here. So it says 9 is 1, 11, 4, 12, 1, 13, 5, so on and so forth. And it goes through, and the top row shows the different values that appear, and then the second row shows the frequency of each of those values, okay? And so we can see kind of these numbers, and we can see there was one student who scored 35 goals and things like that. So that's the frequency distribution. And we can take this frequency distribution and, no, you don't have to be doing this in R right now. Sorry, there was a question. Should we be doing this in R? No, I would rather you just sit and follow along, okay? The lab time is when you should be following along in R and interacting with your TAs and whatnot, okay? Yeah, and I know the first lab always feels a little bit overwhelming, a little bit scary. You're like, what is this R program? Why do we have to use this? You know, we cannot teach statistics without introducing some kind of software because nobody does statistics entirely by hand. So we have to introduce some kind of software. There's different options. We used to use kind of this toy thing called Fathom. There's other things, StatCrunch and stuff. But a lot of times in universities and different places, we are using R. And so we're just introducing you this. We're just scratching the surface of R. But I know the very first time you're typing all of these commands, it's very picky. You capitalize something, you don't capitalize something, and it errors out. It can be frustrating, but But just like everything in life, the first time you try something out, it's uncomfortable and awkward. But then the more you do it, you get better at it. Okay, and you might even enjoy it. All right, what does the function library do? The library, okay, so when you download R, it comes with certain functions built in, and then other functions like tally are not included, okay? So you can kind of think of this as like, like a book of spells, okay? You've got a library full of different spells or functions here, and here we're opening up like a book, or it's called a package called Mosaic, and inside Mosaic there's different commands, and one of the commands is tally, and this gives us access. By calling library on it, it gives us access to this function tally. If we didn't use library Mosaic, then and we say make a tally, R will say tally, I don't know what that is. Okay. Do you need to memorize all of these functions? No, you don't need to memorize them. Okay. So first of all, the quizzes and the exams are open note and open book. Okay. So you don't need to memorize really anything. You can always use your notes and the textbook for reference. But you'll make use of these in the labs, and you know, it could be helpful to kind of just jot down some of the functions that you use frequently. Would I consider putting the lecture slides on CCLE before lecture begins? I could, but I often make edits to my lecture as I'm giving them, as I'm teaching. I realize, oh, you know what, this didn't work out, that worked out. So just a warning that could happen. Okay. I know I've already given the first quiz answer, but I'm going to give it one more time just in case, I don't know, somebody wasn't paying attention for a few minutes. But so the first quiz answer, you should already have this, but the first quiz answer is the letter B as in boy. So that's the first quiz answer, and you should already have this from a few minutes ago. All right, so anyway, what we can do is we can take this frequency distribution and we can represent it graphically using a histogram, okay? So we visualize the frequency distribution with the histogram. So here's the frequency distribution from the previous page, and here it is represented as a histogram. The book also mentions something called a dot plot, where you put dots rather than these bars. But basically what we see is there is a bar centered at 9 with a height of 1. There's a bar at 11, okay, right here, with a height of 4. There's a bar at 12 with a height of 1, a bar of 13 with a height of 5, 14 with a height of 3, 15 with a height of 2. And so all we are doing is we're taking this frequency distribution and we're turning them into bars where the height of the bar represents the count or the frequency that value appears, okay? And then the values themselves show up on the y-axis. So there's a huge, you know, this is a little bit lost in the frequency distribution, but there's a huge gap between 21 and 35, okay? And that gap is represented, is able to be seen visually when you create a histogram out of this. We can see, oh, you know, this person who scored 35 goals, they really are set up far apart from all of the other students here, okay? So between 21 and 35, there's quite a big gap, and that's visualized using the histogram, okay? So histogram is a function that is part of library Mosaic. You give it the vector, and here I specified width equals 1, which means I want each bar to basically represent, to have a width of 1, okay? So that each of these values show up in their own bar. You know, you could change it to say width is, you know, 1.5 or 2 or things like that. And some bars will have a couple values and some bars will only have 1 value and things like that. But that's what we have here. Okay, and type equals count corresponds to basically the count of each of these things. So I can change the width, so we can modify some of these options, all right? and I can change the width to equal 3. This histogram and this histogram both represent the exact same data, all right? The difference is here, the width is 1, which means each bar has a width of 1, and over here, each bar has a width of 3, okay? I think by default, when you specify something like width equals 3, the first bar gets centered kind of at that first number. So our first number that appeared is 9, and so this bar is centered at 9, which means the bar goes from 7.5 to 10.5, right? So half of 3. So if the bar is centered at 3, I mean, if the bar has a width of 3 and it's centered at 9, half of 3 is 1.5. So 9 minus 1.5 is 7.5. And then 9 plus 1.5 is 10.5. And so, so 10.5 to 7.5, that's a width of 3, okay? And if we say, well, how many values are between 7.5 and 10.5? There's only one value between 7.5 and 10.5. So we get a height of 1 for this bar. And then the next bar goes from 10.5, and it's got a width of 3. So it goes from 10.5 to 13.5, okay? And how many bar values are between 10.5 and 13.5? Okay, so if we look at the frequency table, that would be between 10.5 and 13.5, you have all the values at 11, 12, and 13, which is 4 plus 1 plus 5. There's a total of 10 values between 10.5 and 13.5. And therefore, we have the height of our bar is 10, okay? And so, so this histogram and this histogram represent the same underlying frequency distribution, but they look fairly different because the width of the bars have changed. Okay, is width the same as bin? Yeah, so there's a few different options, and I think in histogram, another option is how many bins do you want, okay? So here I'm telling how wide I want each of my bins, or how wide I want these things by specifying width. Another thing is you can say, you know what, don't bother me with figuring out how wide each bin should be. I just want to see a total of 15 bars or 15 bins, okay? And so that's an argument. I think it's n int, number of intervals, n int. You can say like n int is 15 or whatever, and then R will on its own figure out, okay, well, if you want 15 bars, then each bar should be this wide and things like that, and it will figure it out. So they're closely related. Width and bin are closely related, but one is kind of telling you how wide the bins should be, and the other one is telling you how many bins there should be, okay? If one of the numbers were 10.5, would that number be counted twice? The answer is no. I kind of put this, I didn't really mention it when I'm talking, but one of the bars will be 10.5 inclusive. So if 10.5 appears, it goes into this first bar, and then this bar, which starts at 10.5, it's 10.5 exclusive, okay? And I think there's an option you can say, I want the right side to be inclusive, or I want the left side to be inclusive. These are kind of different options you can choose. I think by default, it's right side inclusive. I think with this histogram, if you load up a different library, so this is the histogram that comes with library Mosaic, okay? There's like other other packages that have their own version of a histogram function and things like that, okay? Does it matter? Does it matter which side is inclusive? Not really, not really. How do you know which one to use? Again, it doesn't really matter. Like, does it matter that you present the histogram this way or the histogram this way? Not really. It's a little bit of personal preference, and it's kind of hard to explain other than you know, it's like giving someone directions, like I want you to decorate the table so it looks good, and in the beginning you have no idea what exactly looks good, and but after with some experience you realize, okay, you know what, this is pleasant, this is unpleasant, and things like that. And similar with histograms, you want a histogram that quote unquote looks good, but does this look good? Does this look good? And And a little bit of it is going to be personal preference. And other things will be things like how easy is it to read and things like that. So, so here I just want to show you like modifying the settings a little bit. Again, all of these histograms represent the same underlying frequency distribution, but here I changed one of the settings to be center equals 10. Now what does that do? Okay, so this histogram and this histogram, same frequency distribution, okay? But they look different, okay? And I'm not trying to be deceptive. It's just all we've done is we've changed this first bar, this one right here, it's centered at 10, okay? Over here, it's centered at 9. So the first bar includes values from 7.5 to 10.5. Here, we've created a bar centered at 10, so it includes values from 8.5 to 11.5. Okay, is one of these right and the other one wrong? No, they're both equally valid. They're both correct. And they look a little bit different, but this is just a known phenomenon of histograms, is that based on your original settings, things can look a little bit different. Okay, but here we have a bar centered at 10. So this includes values from 8.5 to 11.5, which will be values 9, 10, and 11. And there's a total of 5 of them. Okay, and the next bar goes from 11.5 to 14.5. Okay, and there's a total of 9 values. Okay, and so this is how the histogram looks like. Right? So these are just kind of the options that I've set. Is that all right? Are you guys doing okay here? Give me a green check mark if you're feeling okay with all of this histogram stuff. All right, great. Thank you, guys. Okay, so here is the histogram, and I'm going to create the exact same thing. All right, and all I'm going to do is I'm going to change this option from count, type equals count, to type equals percent, okay? And the two histograms look almost exactly the same. The only thing that has changed is what appears on the y-axis. Here, this bar has a height of 9 because there's 9 values. The count of values in this bar is 9, okay? And the count of values in this bar is 5, okay? Now, we've got percent of total, and the height of this bar is something around 18%, 17.8. And what that means is that we're just looking at the total number of observations. We have 28 observations in total, and this first bar has 5 observations. So if I do 5 divided by 28, that is 18% of the observations, 17.8% of the observations. And that's what this bar represents. It's got a height of the kind of the percentage there, right? And this can be useful if you want to compare histograms from data sets of different sizes, right? So if one data set has 28 observations, it might look like this or this. And if you have another data set with 1,000 observations, if you used counts, each of those bins will have a height very high because there's 1,000 observations. So using a histogram with just pure counts might not be beneficial in that case. But dealing with percentages, this is what we get. All the percentages will add up to 100%. All the heights will add up to 100. Can you explain how the first bar has 5 observations? Yeah, so in this thing, we have a bar centered at 10, okay? Remember, the bar has a width of 3, okay? So the endpoints of the bar are gonna be 8.5 and 11.5, right? So the width, the difference between 8.5 and 11.5 is 3, and the average of these two numbers is 10, so meaning it's centered at 10, right? If I do 11.5 plus 8.5, that adds up to 20. 20 divided by 2 is equal to 10, all right? So this bar is centered at 10 and it has a width of 3. And if we go back to the frequency table and we say, how many values are between 8.5 and 11.5, okay? We would include all the values at 9, all the values at 11. We would not include the value at 12 because 12 is not between 8.5 and 11.5. So between 8.5 and 11.5, we have 1 9 and 4 11s. Okay, or if I go back to the original data set, how many values are between 8.5 and 11.5, and I can count them. These are the 5 observations that are between 8.5 and 11.5. Okay, and so that's how this first bin has 5 observations, and then when I turn them into relative frequencies, I do 5 divided by 28 observations, and I get 18%. All right, and so that's the relative frequency histogram. Okay, and then there's one more, and this is called a density histogram, right? And conceptually, the density histogram feels a little strange, okay? But the idea here is you're basically taking the relative frequency histogram where you've got a percentage, okay? So this bar has a height of 17.8%, okay? And then what we do is with a density histogram is we take that relative proportion, that 17.8%, 0.178, and we divide by the width of the bar, okay? So our bars have a width of 3, so we're gonna take 0.178 and divide by 3, and we get something just under 0.06. Okay, so if you do 18% divided by 3, you get 6%, and we're doing a number slightly smaller than 18%, 17.8%, okay? And our width is 3, and so we divide by 3, and we get the density histogram, okay? Now, why would we want to do something like this, okay? So with the relative frequency histogram, if you add up the percentages, all the percentages add up to 100. If you add up the heights add up to 100%. Here, if you add up the area, okay, that is the base times the height, or the width times the height of each bar, if you add up the areas, right, you calculate the area of this bar, you do the width of the base times the height, plus the width of the base times the height, and things like that. And if you add up all of the areas, the total area is 1, okay? And for statisticians, we like things where the area equals 1, and so so that's why we've created this thing called a density histogram. It feels a little bit strange, but it appears quite a bit enough that that I at least want to mention it. Okay, so you can think of it as the relative frequency histogram, but we've divided the height by that relative percentage. We've divided it by the width of the bar. So if you have really wide bars, then your density values will get lower. And if you have really narrow bars, like you can even have bars where the width is, you know, like 0.1, that's actually going to make your density even higher. So that's the density histogram. Okay, I apologize for this wall of text, but in your labs, when you call histogram, you might see this tilde operator, okay? All right, and you're like, and over here, I didn't use the tilde at all. I just put in the vector, okay? So the histogram function is able to work with vectors directly. And if you work with vectors directly, you do not need the tilde, okay? You can just do histogram and then the name of the vector, like histogram goals, and it's gonna work, okay? When you load in a data set from, say, reading a CSV file, so in your lab, you're reading in births.csv, when you do that, R creates what you save it as a data frame, okay? And so I think in your lab you call it NC births, okay, North Carolina births. It's being saved as a data frame, and a data frame is basically a table, right? It's got a table, bunch of rows, and a bunch of columns, and each column is a vector, all right? And you can access the vector. You can get the vector of weights using the $sign. So you can say from the data frame North Carolina births, look at the column weight, okay? And that's what this $sign does. So you can say NC births, $sign weight, and that's going to give you just the one vector, which is one column inside the data frame. Is that all right? This idea of accessing a vector inside a data frame using the $sign. Okay, I hope that's okay. All right, and so you can call a histogram on the vector, because this here represents just the vector inside there, right? And so there's no tilde here because I'm just accessing the vector. It's equivalent of this. It's just here that the vector has a slightly more complicated name. You can also, all right, with something like histogram, you can also get the variable by using the tilde, right? And so you can say, you know what? I want to look at the weight variable, and you say tilde weight, histogram tilde weight, all right? And you know what? That variable is going to be found in the data set or the data frame called NC births. All right, so we say NC births, and that's going to be the data. And so this histogram and this histogram command are exactly equivalent. These two things are exactly equivalent. It's just this one uses a different notation where we say, I want to look at this column using the tilde this column from the data set NC births, okay? And the advantage of using the tilde is that it will let you create more complicated histograms, okay? So for example, this has spilled onto 2 lines here, but you can do a weight bar habit, and what this will do is it's going to create basically 2 separate histograms based on the variable habit, which is the smoking habit of the mother. Was the mother smoking during her pregnancy or not smoking during her pregnancy? And it's going to say, here's the histogram of weights of mothers who are smoking. Here's the histogram of weights of the babies for mothers who are not smoking. And it allows you to kind of create these slightly more complicated histograms. And I think you've got an example of this in your lab. And you can really only achieve that using the tilde notation, okay? That's a side note, will be covered more thoroughly in your lab, right? R also has a function called Hist, and it creates a histogram, okay? And histograms can be created with this. It doesn't require the library Mosaic, and you can do quite a bit. It's just controlling how many bins and where the breaks form and things like that requires a little bit more effort when using Hist. It's doable, and you know, if you plan on working with R in the future, you know, this is probably a good function to learn, and learning how to control it is good. But, you know, as far as this intro class, I think using the Mosaic library and kind of the interface histogram there is you know, more desirable. So you know, one complaint, and this is a totally valid complaint that people have about R, is that there's often like 10 ways to do the same thing. You have a bunch of kind of different packages and competing packages and libraries, right? It's kind of just like asking somebody, you know, how do you make lasagna? And depending on which cookbook you pick up, you're going to get slightly different lasagnas, right? And so depending on which package you're using, which library package you use, you might get a different recipe for a lasagna, or a different function for a histogram, or a different function for a histogram, and things like that. And so, you know, some people just want, hey, you know what? I don't want to have to deal with 10 different ways to make a histogram. Just give me one, okay? And R is not really the language for that, right? We like R embraces the idea of kind of different kinds of, I don't know why I'm going with this analogy here, but different kinds of lasagnas, right? Like someone might like lots of cheese, I don't know, whatever. Okay, you know, people have different preferences, and people might have different preferences regarding how their histograms look and how they operate them. And so there's different libraries and different versions of the thing, okay? But yeah, for the newcomer, you know, you might say, you know, my life would be just easier if there was just one thing to do it, and I didn't have to be confused and look up at all the differences, okay? It's true, but R kind of embraces just the open source nature that people can kind of make different versions of things. All right, I'm going to go ahead and load up the North Carolina birth data into R, so we do that using a function like read.csv, and I think this appears in your lab as well. So I've got the CSV file births.csv, and I say read.csv, the file name is births.csv. Of course, you have to have this in the same directory as your working directory, and I think you've covered that in your lab as well. And I'm going to store this into the object nc births, okay? And here's a function called str, which shows the structure of the data. And the structure of the data is that it shows off all the variables that appear. So we've got, the variable gender and preemie and weight and APGAR and father's age, father's education, mother's education, all of this stuff, okay? And we've got, different values here. All right, so we'll take a look at this here. All right, so here is a histogram of the mother's education level. All right, and so this is mother's education is basically the number of years of formal school, right? So so this is what it looks like. Okay, and in here I said width is equal to 2, and we've got a relative frequency one using type equals %. Right. And this is what we call a density curve. You don't have to worry. I intentionally left off the command to create the density curve, so you don't have to worry about making this yourself. But this is kind of a smooth line representation, right? So if you had to summarize this histogram with kind of a smoothed out line, what would it look like? The smooth line representation might look something like this, okay? So this is what we call a density curve, and here is the histogram itself, okay? So this is the histogram, this is the density curve, right? And I think we can see how to go from here to here, right? So I think it looks reasonable, okay? Here is another histogram. This is the distribution of weights of full-term babies, okay? So in this case, right, so the North Carolina births data set has like I guess 1,992 observations, about 2,000 observations on 21 different variables. And there's this variable called preemie, which means the baby was born premature, or it was, and it's either going to be a yes or no. Okay, so if you ever have children, a pregnancy is supposed to be around 40 weeks, and if the baby is born before 38 weeks, okay, so 37 weeks or less, it's considered to be born premature. It's born a little bit earlier than expected. And so we would say preemie is yes, and in general, babies born premature weigh less than babies born full term. Full term babies are anything that's born 38 weeks or after, okay? And so what I'm doing in this command is I'm saying, you know what, I don't want to look at the entire North Carolina births data set. I want to look at a subset. I want to look at the subset where where it is not a premature baby. So I'm going to say preemie is equal to no, right? Because the preemie values are either yeses or nos or things like that. So we're going to say subset preemie equals no, okay? And when you specify a condition, when you do a subset, you have to use 2 equal signs here. All right, so I'm going to say, you know what, don't look at the entire data set, but only look at the full-term babies, okay? And then let's look at the weights. Let's look at the weights of those full-term babies. And this is what the distribution looks like, okay? And again, if I create a density curve out of it, it looks something like this, right? So here's the histogram that represents it, and here's the density curve. All right, so I use these distributions because they illustrate certain ideas that are useful for us when we talk about describing the shape of the distribution, right? And so one concept is modality. Modality is basically how many peaks are there in the data. If there's one peak in the data, we say it's a unimodal distribution. If there are two peaks, we say it's bimodal. And if there's more than two peaks, we'll often say multimodal. I guess you can say trimodal or quad, I don't know, tetramodal, quadmodal, something. I haven't really heard of that. So we'll usually just say multimodal, where more than two peaks. So when we look at mother's education, we would say this is bimodal. There's a peak here, there's a peak here, okay? And if we think about that, and we say, well, this is years of formal schooling, it kind of makes sense, right? We're gonna see a peak at 12. This is everybody who finished high school, okay? You get 12 years of education when you finish high school. And then we have another peak at 16, and that's people who finished college, okay? And, you know, you can get more schooling than that, but apparently there were not a lot in our data set of around, you know, under 2,000 people to observe such a thing. So we get two peaks, probably corresponding to kind of completed high school and completed college. All right, and so we get a bimodal distribution here. Whereas when we look at the weight of full-term babies, it's unimodal, right? So one peak, and this is, looks to be around 120 ounces or something, so around 7 something pounds. This is, and so this just means one value is kind of the most common weight for babies born. Some babies weigh more, some babies weigh less. This is kind of what we've got. So that's unimodal, and this is bimodal, all right? We have, there's another idea here, and that is the data symmetric or skewed, all right? If the left and right-hand side of the data look similar, we would say the distribution is symmetric. And if there's a long tail, we say the data is skewed. If the tail's on the left, it's skewed left. If the tail's on the right, it's skewed right or right skewed. So if we look at mother's education, the tail is basically a skinny, this part that kind of drags on, this part, we call this the tail. All right, and the tail is on the left-hand side of the graph. And so we would say this is left skewed, okay? And so basically what this means is that, you know, the bulk of mothers have a kind of certain number of years of education, and some, you know, didn't get many years of formal education for one reason or another. And you know, there's not many, but there are enough to kind of register on the histogram. And so so we say we have a tail over here, and it's on the left because smaller numbers appear on the left. If you had a tail over on this side, we would say it's right skewed. Okay, so this would be skewed left or left skewed. And over here, we can kind of draw a line in the middle, and we would say this thing looks pretty symmetric. And so we would say this distribution is symmetric. It's very rare to find a perfectly symmetric data set in real life, so this is about as close as you're going to realistically find. And we would say this data set is symmetric. Okay. Also, if you create a display, anything that looks unusual compared to everyone else could be considered an outlier. So, you know, if we go all the way back to the soccer goals, you know, here we have one person who scored 35 goals, and that is quite unusual compared to everyone else who scored between, you know, 9 and 20 goals, 21 goals. Person who scores 35, that's unusual. this might be considered an outlier. All right, how are we doing? Are we doing okay? All right, great. Let me give you the second quiz answer. Second quiz answer is D as in dog. Second quiz answer is D as in dog. Okay. I hope you guys got that. Second quiz answer, D as in dog. Let's talk about bar charts. Okay, bar charts are for categorical data. All the histograms that we've done so far, those are all numeric data. When we talk about categorical data, we use a bar chart, okay? When you create a bar chart, it does not make sense to talk about things like, is the data symmetric or skewed or unimodal? Because when you create a bar chart, the bars can be rearranged, okay? I think by default, when it makes a bar graph, it will put them in alphabetical order, but any other order is just as valid, okay? So, so here, in the data set, the North Carolina births data set, you know, we have these kind of dichotomous things. And so, you know, in 2004, when they were recording genders for these babies, they were recorded as male or female. And I understand that, you know, gender is not necessarily a binary thing, but this is what appears in our data when we have male and female, and this is how a bar graph gets represented. Your Wi-Fi broke up. Yeah, the second quiz answer is D as in dog. D as in dog. That's the second quiz answer here. Okay. And all right. So here is the here's a bar graph, and here female appears on the left and male appears on the right. But if somebody wanted to swap the position of these bars, perfectly valid and fine. So so there's no requirement regarding the order or the arrangement of these bars. Okay. Here is another bar graph, and regarding the smoking habit of the mother during pregnancy. And so here, when we're talking about smokers versus non-smokers, this is how the bar graph gets represented. And if you had more categories, you would have multiple bars here. Okay. So so this is what we have. All right. So here's a question: which variable shows more variation, gender or smoking habit? Okay. So as far as the variation in the variable, okay, does baby gender show more variation, or does smoking habit show more variation? What do you guys think? Let's say if you guys think gender shows more variation, choose green yes, and if you think smoking shows more variation, choose red no. Okay, so this is for smoking, and this is for gender. So which one shows more variation, gender or smoking? Okay, so green for gender, green yes for gender, red no for smoking. Okay, so it looks like a lot of you, about 53 of you, are saying smoking shows more variation and gender shows less variation. So about 6 or 7 of you say this. Okay, the answer is gender. Gender shows more variation. Which one shows more variation? The answer is gender. Okay, so, and you say, well, how is that possible, right? Like, these two bars look like they're the same height, and these two bars are very different in height. So this feels like this has way more variation than this one. Okay, that's, it is true. This bar and this bar are different heights, and this bar are similar in height. But when we're talking about variation in a categorical variable, we're talking about the values that appear in the data set itself. Okay, so you know, so you can think of this as almost like diversity. Okay, maximum variation happens when all of the categories are equally represented. Okay, so when you have so you can imagine going to a, so if you have a major that is dominated by one gender, okay, and there's very few, we would not say that like, if you imagine, you know, this was a major, some major at our school, and this was one of the genders, and this was the other gender, again, fully understanding that it's not necessarily a binary thing, you know, we would not say that, we would say there is a diversity issue with this gender, right? We'd say, you know, we want, you know, we want more representation of whichever gender this is, okay? And so, so that's basically what we've got going on, right? So you have maximum variation when all the different categories are kind of equally represented. And if there's just one category that's kind of shows up all the time, and there's very few of any of the other categories, that actually has less variation. Okay, and that's basically what's going on here. Okay, so when one category is much more prevalent than any of the other categories, there's less variation in that variable, right? So that's kind of the idea of variation when it comes to a categorical variable. Okay, it's not referring to whether the counts, okay, we're not talking about the heights of the bars. Are the heights of the bars different? Or actually, for the categorical variable, we don't want different heights. Anyway, for the categorical variable, yeah, we want heights to be fairly similar if we want maximum variation. Okay, why don't we take a short, I don't know, 5-minute break here, okay, and then we'll come back and we'll do chapter 3, and again, the second quiz answer, I'll do this right before our break. Second quiz answer is D, and again, you know, when the purpose of these quizzes is to get you to watch the lecture and kind of pay attention as you're watching, and don't. So again, please don't share the quiz answers. You're not helping out your fellow students in their learning. You might help them get the points that they need for the quiz, but that's not the goal. Okay, the goal is to get you guys to learn. Okay, so I'm going to go ahead and just pause the recording for a couple of minutes. We'll come back in about and we are going to look at chapter 3. Okay. And so chapter 3 is a bunch of number stuff. In particular, we're looking at numeric summaries, okay? So we're gonna look at things like the mean and the median, which I think you guys are already familiar with. We'll also look at the range, IQR, variance, standard deviation. I think you guys are probably already familiar with range, but then the other ones you might not be familiar with. Z-scores and box plots, we'll also talk about those. When will the Gradescope quizzes be up? So Gradescope quiz 0 is already up, and that is due tonight at 11:59. And then Gradescope quiz 1 is going to open up basically after lecture today, and it closes on Friday. Now make sure you don't click that link and open it up until you're ready to take the quiz, because you get 1 hour and it's timed. So when you click it and you open it up, your time starts ticking. It's due 11:59 California time, 11:59 p.m. on Friday, California time. So so again, make sure you don't open up that quiz until you're ready to take it. So you know, do your homework and study a little bit, and then you can start working on it. Okay, and again, if you do bad on a quiz, or you feel like, oh my gosh, I don't know how to do any of this stuff, the quizzes are intended to be low stakes, okay? Each quiz is worth a total of 3%. So even if you like only get half the points or something, it's not going to significantly impact your grade, okay? But what it does is it gives you exposure to some tough problems, and should help in your preparation for, you know, the midterm and final exams, which will be higher stakes exams. So, you know, of course, studying, you want to do as well as you can on the quizzes, but they're intended to be low stakes, and you don't have to stress or worry too much if you do poorly on one of the quizzes. And also, your grades, in the grand scheme of things, your grades are not important, okay? You as a human being are much more than your grades or your academic performance. I know it feels good to get good grades, and I know you guys all got into UCLA because you got good grades in high school or good grades at your community college when you transferred in and things like that. And I know it feels good to get good grades, but you as a human being in your life is so much more than the grades you earn. And you know, at a place like UCLA, you were surrounded by other brilliant students. Everybody else was also got very good grades in their high school or community college, and that's why they're also here. So it's easy to fall into the trap of comparing yourself to others. Don't fall into that trap, okay? You're much more than your academic performance. Okay, are your quizzes more intense than the homework? You know, it's hard for me to answer this question, you know. I don't think so. I think my quizzes are about as intense as maybe some of the, you know, more challenging homework problems, right? So the homework problems range in difficulty from easy to, you know, a little bit more involved or a little bit tougher. And I think my quiz questions kind of range from moderates to difficult homework. I don't think they're not a huge step beyond what you see in the homework. So that's my opinion. Now if I'm out of touch with reality and my quizzes are way harder than what appears in the homework, then, you know, please let me know, and we can make some adjustments. Okay, let's get on to numeric summaries. Okay, numeric summaries allow us to describe an entire distribution. Remember, an entire distribution is your full set of data. So you might have, you know, for the North Carolina births, that's 1,992 babies, okay? These are you know, if you think about the data, what they represent, they're actual real life people that were born in North Carolina in the year 2004, or what is it, 2012? I forget, 2012, okay? So they're all turning 8 years old now. These are real kids, real lives. But, you know, we've just kind of summarized their birth story down into a few numbers, right? And we got 1,992 of these observations. And then we're further going to summarize that with just a few numbers, okay? And so numeric summaries, by definition, is reductive, okay? We leave out the details, okay? And it's useful to do that when you want to make quick comparisons between different samples, right? You want to make a comparison between, you know, what were the births like in North Carolina in this year versus the births in, say, Florida or whatever, okay? Is there a difference between these? Is there a difference between these? And rather than getting bogged down with the details, you can look at these kind of numeric summaries. And so they're useful in that sense, but they are reductive, right? And so today we're going to look at summaries like the mean and the median, summaries for the spread like range, IQR, standard deviation, variance. That's all in there, okay? Here's just some other examples of numeric summaries. And we've got, so for example, there's the GPA and Rotten Tomato score, okay? So the GPA reduces your entire academic career, right? All the hard classes you took, the easy classes you took, your triumphs and failures. It just boils it down to a single number, right? It says, boom, your time at UCLA can be summarized with 3.7. And you're like, oh, well, that feels very reductive. And it is, okay? it's useful when you're making quick comparisons between students, but as far as admissions go, you don't want to base your entire admission strategy based on GPA alone because it is so reductive, right? But at a quick glance, it's useful, right? Rotten Tomato score, you're looking at movies, and it kind of takes the proportion of critics who liked a movie or didn't like a movie. And of course, it misses a whole lot of other things, right? You can get a movie with a 98% rating, but if it's in a genre you don't like, you're probably still not going to enjoy it, right? Like if you don't like horror movies, it doesn't matter if the movie has a 98% Rotten Tomato rating. You're not going to like the movie. So that's what we have, right? Tell that to medical schools. Yeah, so so the issue with medical schools is they get so many applications that they often do a first pass, and they just look at your GPA and they say, oh, everybody below a certain GPA, let's just throw them away. Let's make our lives easier, because they don't want to look at all bajillion applications. They just want to look at they only feel like reading a few of them. So numeric summaries are helpful in that, I think inherently people are a little bit lazy and they don't want to look at all of these details, and our brains can't handle all the details. So they do kind of a first cut, and then they look at things a little bit more closely. But yeah, it is very reductive. Better or worse, we have numeric summaries. They certainly are useful, but making your life rely entirely on numeric summaries is a very dangerous thing. Okay, you lose a lot of nuance. Okay. All right, so when we talk about summarizing the center, we basically have the mean and the median, okay? And I think you guys are familiar with these, okay? The mean can be thought of as a balancing point, or the center of mass, right? So if you got a histogram and you place it on a seesaw, you want to know, like, where is the seesaw? Where should I put the little fulcrum, the balancing point, so that the histogram ends up balanced? That's going to be the mean, okay? The median, on the other hand, is the middle point, which is the spot where half of the values are less than or equal to the median, half of the values are greater than or equal to the median, okay? And in R, if you have a vector of numbers, you can find the mean using mean of the vector. You can use median of the vector. And if you have a data frame and you need access to a vector, you use the dollar sign. All right, so let's take a look here. So here I've got, we're gonna take the North Carolina births, we're gonna subset it to only the full-term babies. And we're gonna say, what is the mean of the full-term babies' weight, okay? And the mean is 119.5964. And if I put that here, this line, this vertical line represents the mean. And if this graph were on a seesaw, and I put a little triangle right here, then our thing would be balanced. All right, here is the median, okay? So if I do a median of the weight, okay, full term dollar sign weight, and I ask what's the median is 119, all right? And this is where it gets plotted. And this means about half of the babies, so I've got a total of 1,992. So half of that is like what, 996, okay? 996 values are 119 or less, and I've got 996 values that are 119 or more. And that's the median. All right, here's a data set that I'm just bringing up out of nowhere. This is, we're looking at Major League Baseball players. This is the Lahman data set, okay? So I can load up the library by calling just library Lahman. Lahman is this guy who collects baseball data, all right? And so there's a data set, a library. And so this opens this up, and we can load up basically a table from this package here called salaries, and this contains all the salaries of the different players. So it's got, you know, Mike Trout, who gets paid, I don't know, however $1 million per year, but he gets paid a lot, okay? And then everybody in between, and you know, your rookies who probably get paid the league minimum. And so this is what we have, and you ask for the mean. What is the mean salary? So here I subset all the salaries. This contains like many years of salaries, and we're just going to say let's look at 2018. Okay, let's look at 2018, because if I did 2019, I think it's going to be weird and messed up because no, 2019 finished, but 2020 it's all weird because I don't even know if we're going to have a baseball season. 60 games, maybe not. Okay, but anyway, so we'll look at the 2018 salaries. We ask the mean, and the mean, this is a hard number to read, but it's basically 2 million, 2.08 million, and this is the mean. And if we were to put this thing on a seesaw, and we ask where's this thing going to be balanced, we would put the little triangle, the little fulcrum right here at this line here, and that's where this histogram would be balanced. Okay. If you ask for the median salary, okay, what's the median salary? The median salary is 550,000, 550,000, which means half of the baseball players make 550,000 per year or less, and half of the baseball players make 550,000 or more. Okay, so this is Major League Baseball. This is the highest level of baseball that you can play in pro ball. And so there's a huge difference, right? The mean is 2.08 million. That's almost 4 times as much as the median, which is 550,000. Okay. So you know, that's one thing that's quite different. Okay. When the data is symmetric, the mean and the median are going to have very similar values, right? So when we looked at this symmetric data, the mean was 119.5964, and the median is 119. Over here, the mean is 2.08 million, and here the median is 550,000. Okay, so when the data is skewed, the mean gets pulled in the direction of skew. So here we have a right skewed data set, right? There's a tail going off to the right. The mean is going to be greater than the median when it's right skewed. If the data is left skewed, the mean gets pulled in the direction of the skew, and that's going to make the mean less than the median. Okay. So the baseball salaries are very right skewed. Pretty much all income distributions are very right skewed. And maybe that's, well, anyway. So it's very right skewed. And so, you know, most of the players make less than $1 million per year, and the median is 550,000, okay? Whereas the mean is much higher at around 2.08 million. Okay, so that's just something to keep in mind here. Okay, to get the mean, I think you guys already know how to do this. You add up all the numbers and you divide by how many you have. That's how you find the mean. The symbol is X bar. The median is you arrange the numbers in order, and then you find the middle number. That's how you find the median. Okay, and we don't have a universally accepted symbol for the median. We just often call it the median. Okay, so that's how we might describe the center or the typical values in a distribution. The other idea we want to talk about is spread, okay? Spread describes whether the values are similar to each other or if they're very different from each other, right? Are the values similar or are they very different, right? So I want you to imagine kind of the following 3 rooms. And so I'm going to just do them one at a time, and we want to think about the ages of the people in the rooms, right? So imagine a 2nd grade classroom. What kind of ages will you see in a 2nd grade classroom? Okay, so in the US, in 2nd grade, you're in 2nd grade when you're about 7 years old, or you know, or you might turn 8 while you're in 2nd grade. Okay. And so nearly all of the ages of the students in 2nd grade will be 7 or 8, okay? All right, what about this class? Okay, Stats 10, all right, so imagine we were on campus, we were in a classroom and we could look around and we could talk about the ages of the students in our class. Okay, what are the what's the spread of the ages in the students in a class? So a lot of students, you know, are between first and fourth years for Stats 10. And a lot of students came straight out of high school to UCLA, or they went to community college, spent 2 years there, and they transferred. And so you're going to have a lot of students between 18 and 22, but then you also have a lot of students who did other things before coming to UCLA, or they took a little bit longer at community college, or they had military service, or they're coming back as an adult. And so you have a lot of students quite outside of that range as well, okay? And so you've got more spread for the Stats 10 students, okay? And then also imagine the waiting room at the DMV, okay? So, when you register for your driver's license, or you renew your vehicle registration and you have to get in line there, what is the range or the spread of ages there, okay? There you've got all kinds of ages. You have teens, you have adults, you have seniors, you have children of the parents waiting, wide range of ages, right? And so, so this would have the highest amount of spread, okay? And so we would say the second grade classroom has the least amount of spread in the ages. Stats 10 classroom has a medium amount of spread. The DMV waiting room has the most amount of spread, right? And instead of using vague terms like little spread and lots of spread, we can use a numeric summary, which will actually put a number, and we'll say something like the second grade classroom has a standard deviation of 0.4 years. The Stats 10 classroom has a standard deviation of 1.7 years, and the DMV waiting room has a standard deviation of 16 or something like that. You have a number to quantify the amount of spread, okay? And all of these things, the variance, standard deviation, range, and IQR, are ways for us to quantify the spread. But again, the concept of spread is just, are the numbers quite similar to each other, or are the numbers quite different from each other? And a lot of you guys kind of were thinking along those lines when you were thinking about the variation that appears in the bar graphs, because you were looking at the different heights of the bars. But it turns out for the categorical variables, that's not what we want. But when we're talking about a numeric variable, that is what we want. We want different kinds of values, not the same values or similar values. We want different values as far as, I shouldn't say that's what we want. That's what variance or spread refers to. Spread refers to, are the values different or are they similar? All right, so there's two terms, variance and standard deviation, okay? And the variance, you can think of this as the quote-unquote average squared distance from the mean, and we'll break that definition down in a moment. And the symbol for the variance is s squared. And then the standard deviation is the square root of the variance, okay? And the symbol is s. Okay, so we don't really have a symbol for variance. It's just you take the standard deviation s and you square it, and that gives you the variance. And we'll look at this definition for variance: average squared distance from the mean. Okay, here's a couple formulas. Again, you don't have to memorize these. The quizzes and the exams are open note and open book, and we can look at all of this formula stuff. But I just kind of want to get into, I think it's easier to remember average squared distance from the mean rather than memorizing this, although this also represents quote-unquote average squared distance from the mean. Okay, so let's say we have the numbers 1, 2, 3, 10, and we want to find the variance, which is the quote-unquote average squared distance from the mean, okay? The mean of these numbers, the mean of these numbers is 4. That's a typo. Okay, so this should say 4. The mean of these numbers is 4. 1 plus 2 plus 3 plus 10 is 16. 16 divided by 4 is 4. Okay, the mean of these numbers, this should say 4. The mean of the numbers is 4. Okay, And then, so then we say, well, what is the distance from the mean and what is the squared distance from the mean? So we're going to look at each numbers, 1, 2, 3, 10, and we're going to say, what is its distance from the mean, which is 4, and what is its squared distance from the mean, okay? So the number 1, how far is it away from 4? It's 3. It's 3 units away from 4, okay? So 1 is 3 units away from 4, and so if you take 3 and you square it, you get 9. How far is 2 from 4? It's 2 away from 4. And if you square 2, that distance, the distance from the mean is 2. You square that, you get 4. What is 3's distance from the mean? 3 is 1 away from the mean, 1 unit away from the mean, 4. And so you square that, you get 1. And 10 is 6 units away from the mean, 4. Okay, so the distance from the mean is 6. And if you square 6, you get 36. All right. Is that good so far? Okay. And so what we do is we're going to take the average of these numbers. The squared distances are 9, 4, 1, and 36. Okay. Now, typically when you do the average, you add them up, or you take the mean, you add them up, and you divide by how many numbers you have. Now, for reasons beyond the scope of this course, meaning you don't have to worry about it, we divide by n minus 1 rather than n, okay? If you're interested, and if you're gonna major in stats, you've got to learn this, but if you're not gonna major in stats, you don't have to worry about it. It's called Bessel's correction. You can look that up on Wikipedia. But just for reasons, we're going to divide by n minus 1 rather than n, okay? And so when you take the mean, you would do 9 plus 4 plus 1 plus 36, okay? And that adds up to 50, okay? And if we wanted the mean, we would do 50 divided by 4. But again, for the variance, we're going to divide by n minus 1. So we do 50 divided by 3, and that gives me 16.6667. And this is the variance of these numbers. So here's the numbers. And what we did was we found the mean of these numbers, which is 4, and we're taking the squared distance from the mean. So we found the distance from the mean and we squared it, and we're taking the quote-unquote average, which is adding them up and dividing by n minus 1. And we get this variance, 16.667. All right, if that feels okay, give me a green check mark. And if I totally lost you and you have no idea what I was talking about, give me a red X. Okay. All right, well, thank you to my brave student who gave me a red X. All right. Is there anything in particular? Oh, no, somebody, they took it away. Okay, so maybe it was a misclick, or maybe somebody actually is struggling a little bit. I don't know if you're able to articulate your question, you can put it in the chat, or if not, you can come to office hours and I'm happy to work through this with you, but we'll keep going here. Okay, so so again, we're taking the variance can be thought of as the average squared distance from the mean. So we find the mean, we find the distances from the mean, and then we square those distances, and then we take the average. But again, for reasons beyond the scope of our course, when we take the average, we divide by n minus 1 rather than n. All right, the standard deviation is the square root of the variance. All right, so if we have the numbers 1, 2, 3, 10 from the previous page, the variance is 16.6667. And then we just take the square root of that and we get 4.08. So the standard deviation of these numbers is 4.08. All right. In R, you can get the variance and standard deviation using var and SD. So you create a vector, 1, 2, 3, 10, and you say, what's the variance of this vector? And you get 16.667. And you say, well, what's the standard deviation of this vector? Standard deviation of the vector. And we get the same number, 4.082483. So that's so it's very quick and easy to do, find this mean and standard deviation. All right, so here's just an example. Here we've got two families. Both families have 5 children, and in both families, the mean age of the kids is 9. So the Baker family, the kids' ages are 1, 3, 9, 13, 19. And if you add them up and you divide by 5, you get the average age is 9. Okay. Cook family, the children's ages are 7, 8, 9, 10, 11. And again, 5 kids, the average age is 5. Okay. And so, or I'm sorry, the average age is 9. Okay, you add this up, you get 45 divided by 5, and you get 9. All right, and so if you just look at this, it's very clear that the Baker family kids are a lot more spread out, right? This kid's going to college while there's a baby at home, right? This could happen, right? If the mother had her first child at age, say, 18 or 19, and then their last child at age, 36, 37, it's quite possible to have this kind of range in ages, right? You could also imagine another family where, 1 year right after the other, they had 5 children right in a row. So these kinds of things could happen. And anyway, it's going to be reflected when you calculate the standard deviation. So rather than just saying Baker family, lots of spread, Cook family, little spread, to get the full picture, we can ask, what's the standard deviation? So we just create a vector of numbers and we say, what's the standard deviation of the Baker family? We get 7.35348. Standard deviation of the Cook family, 1.5. Okay, and we can say, okay, bigger standard deviation, smaller standard deviation. And that's that. Okay. All right, another way to measure spread is range. You take the biggest value, maximum, subtract off this minimum, and that's going to be the range. If you got any outliers, like an unusually large value or an unusually small value, that's going to greatly affect the range. Okay, so just be aware of that. The IQR is the interquartile range. All right, and the difference, it's the difference between the 3rd quartile and the 1st quartile. Okay. All right, I'm going to give you your 3rd quiz answer. 3rd quiz answer is A as in apple. A as in apple. That's your 3rd quiz answer for today. I hope you stick around and not just drop out as soon as you get your 3rd quiz answer. So your 3rd quiz answer is A as in apple. Okay, so the IQR is Q3 minus Q1. Q1 is the 1st quartile. That's equal to the 25th percentile. That means 1/4 or 25% of the data is less than or equal to the 1st quartile. And Q3 is the 3rd quartile or the 75th percentile. 3/4 or 75% of the data. So 3/4 is kind of where we get 3rd quartile. 3/4 of the data is less than or equal to the 3rd quartile. So, so here's a quick example. Let's say we've got 12 test scores and I've put them in order from least to greatest, going from 65 to 100. And let's say we want to find the IQR, right? So step 1 is we got to find the median, okay? With 12 scores, we want the median is going to be 6 values are less and 6 values are greater. And so the median is going to be 83.5. These are our 2 middle values of 82 and 85. The mean of these 2 values is 83.5. And so the median is 83.5. We've got 6 values that are less than 83.5. And we've got 6 values that are greater than 83.5. So that's our median. Once you find the median, which I've split here, okay, we can take this and find the quartiles. Okay, so I've got 6 values below the median, and basically I'm going to just split this in half. I'm going to find the median again, and that's going to give me the 1st quartile. So I've got 6 numbers here, and if I split this into half, which will be 3 less and 3 greater, no, that was my that was my kid saying "mommy, mommy" in the background. So yes, I think most everybody is muted, and that was mine. That was my background noise. So so sorry about that. Yeah. Okay. Yeah, my bad. The kids are playing outside, but the little one came inside. So anyway, we've got six values here, and we're going to split this in half. We're going to find Q1. We've got 3 less and 3 greater, okay? And so Q1 is going to be the value between 75 and 77, which is 76, okay? So that's going to be Q1. Q1 is 76, and we got 3 values less than 76, 3 values greater than 76, but less than the median. Same thing with up here. I got 6 values. I'm going to split this in half between these 3 values and these 3 values, and the Q3 is 92, okay? So the IQR is Q3 minus Q1. Q3 is 92. It's the between these two numbers right here. It's going to go right here. That's 92. Q1 goes right here, which is 76. Okay, 92 minus 76 is 16, okay? If we wanted to find the range, you would take the biggest value, 100, subtract off the smallest value, 65, and you get 35. Okay, 92 minus 76 is 16. Our IQR is 16. Our range is 35. All right, so that's the IQR. I hope that's okay. There's something called the 5-number summary, and it consists of finding the minimum, the Q1, the median, which is equivalent to the second quartile. You could call the median Q2. I don't think anybody does that. But you've got Q1, Q2, Q3, and technically the maximum is Q4, the 4th quartile. And the minimum could also be Q0. But I don't think nobody really calls it that. So you got the min, Q1, median, Q3, and maximum. That's known as the 5-number summary. Okay, you can get the 5-number summary in R just by calling summary, okay? Now, for whatever reason, again, for reasons you don't need to worry about, okay, R technically finds the quartiles using a slightly different method than what I showed you, okay? And it technically finds the 1st and 3rd quartiles slightly different, okay? If you want to find the quartiles the way that I just showed you on this previous slide, which is the way the book teaches and the way most textbooks teach, you can call summary and say quantile type 5, and it's going to find the quartiles the way I have described in the slides. Okay, the default behavior of R works a little bit different. Not to worry, okay, but that's what it has. I mean, the numbers are generally going to be very close to each other, especially if you have a very big data set. These numbers are almost going to be identical for a big data set. But for something like this, you might get something where it's a little bit different. Okay, there's something we need to talk about z-scores. We got about 10 minutes left, and I think I can pull this off, okay? Z-scores is useful. Z-scores are useful for determining whether an observation is unusual or not unusual, okay? And it's basically how far is an observation from the mean, which will tell you, like, is it way above the mean or is it way below the mean? You find the distance from the mean, except you're going to express that distance in terms of standard deviations. So if there's lots of spread, a distance might not be that big of a deal. Okay. On the other hand, if there's very little spread in the data, like almost all the numbers are identical, it would be kind of a big deal, right? So finding like somebody who's 80 years old, that's an old person, but seeing an 80-year-old in the DMV waiting room is not unusual, okay? Because the spread in the DMV waiting room is very high. So seeing an 80-year-old in the DMV waiting room would not be surprising, okay? The average age in the 2nd grade classroom is 7, 8, something around there, okay? If you see a 12-year-old in a 2nd grade student, okay, even though 12 is only maybe like 4 years above the average, 4 or 5 years above the average, that would be very surprising to you because the spread in the 2nd grade classroom is so small that anything where you're getting more than that, like seeing a 12-year-old enrolled in second grade, that would be rather surprising, okay? So seeing an 80-year-old, which is, well above the average age, probably is not unusual in the DMV waiting room. Seeing a 12-year-old in the second grade classroom is very unusual. And the Z-score is going to reflect that. Why does it output the mean when we call the function to get a 5-number summary? Oh, that's just what R does. So R, when you call summary, it gives you the 5-number summary plus the mean, because the mean is often a value that we're interested in. So that's all. R just says, I think you want this, right? It says, you want the 5-number summary, and I think you probably want the mean also, so it just gives it to us, okay? That's just how it's programmed. All right, so here's an example, Olympic decathlon. All right, what's more impressive? A long jump where the person, so track and field, person runs and jumps, and they jump 7.4 meters. That's really far, okay? Is that super impressive? Or or is the high jump where they jump 2.2 meters, like they're jumping off the ground, they're getting their body like almost 7 feet high in the ground. Is that more impressive? Okay. Wow. I don't know, right? So what you need to know is you need to know something like, well, what's the average performance? Okay. So maybe the average performance of the long jump is 6.5 meters and the average high jump is 1.88 meters. Okay. I'm just making these numbers up, by the way. I'm just using them for an example. Okay. So 7.4 is 0.9 higher than average of 6.5. 2.2 is 0.32 meters higher than the average of 1.88. Okay, but this distance, 0.9 and 0.32, in of itself doesn't tell the whole picture, because we need to know how much spread there is in our system. Do you have any of these RStudio calls in your quizzes? No, I don't. At least for the very first quiz, there's no RStudio or R on the quiz. So I'm quite sure. So no, okay. And again, definitely I recommend you do your homework before you open up the quiz, okay? So anyway, here's the long jump, here's the high jump, and which feat is more impressive, okay? So what we need to know is we need to know the standard deviation. So we're gonna say, again, I've made up these numbers. We're gonna say average long jump is 6.5 meters and the standard deviation is 0.4. The average high jump is 1.88 meters and the standard deviation is 0.11 meters, okay? And so if a person has a long jump of 7.4, their Z-score, we do 7.4 minus 6.5 divided by the standard deviation of 0.4, we get a Z-score of 2.25. This person with a high jump of 2.2, the Z-score, we do 2.2 minus 1.88 divided by, oh, sorry, this is a typo. This should say 0.11. The calculation's correct, but I have a typo here. 2.2 minus 1.88 divided by 0.11 is 2.909, okay? And so this Z-score of the high jump is bigger than the Z-score for the long jump, and therefore the high jump of 2.2 meters is more impressive than the long jump of 7.4. Now don't get me wrong, both of these are very impressive feats of human athleticism, but this one is more impressive, okay, when you take into account the average and the standard deviation, okay? Again, I made up these numbers, so don't look up Olympic records and say, well, that's not impressive at all. I made them up, okay? But but if these were the numbers, then these would be the Z-scores, and we would say this one's more impressive. There's something called the empirical rule, and basically it says most of your observations will have Z-scores between 1 and -1, so over half, 68%, okay? And then the vast majority, 95%, will have Z-scores between 2 and -2. And almost everyone has a Z-score between 3 and -3. So, so a Z-score that's bigger than 2 or more negative than -2, less than -2, is considered unusual. And Z-scores greater than 3 or less than -3 are considered to be highly unusual. Okay, on its own, the z-score is not particularly helpful. Actually, all z-scores are on the same scale, so z-scores in of itself are useful. Okay, so knowing a number like long jump 7.4, that is not useful in of itself. But as soon as I tell you it has a z-score of 2.25, that gives you some context. You can say, well, greater than 2.25, that's an unusual score, okay? And then as soon as, if I tell you high jump of 2.2, that's not helpful because we don't really know what that means. But if I give you the z-score by itself, just I say the high jump has a z-score of 2.9, you can say, ooh, that's quite high. It's almost at 3. When it hits 3, we would consider that highly unusual, and 2.9 is pretty close to that. So we'd say, all right, 2.9, that's quite impressive. So z-scores on their own are actually helpful. They can be, because they're all on the same, quote, scale. Okay, all z-scores are on the same scale. And so if you hear someone has a z-score of 3.5, you go, wow, whatever we're talking about, they are really out there, okay? And a z-score of, 1, not that impressive, whatever you're talking about, okay? Why is this more important than how much it is above average? Again, something above average may or may not be quote unquote impressive, okay? Or may not be that unusual, right? If there's a large amount of spread, it might not, okay, might not be that unusual. So if we're talking about, I'm trying to think of an example. I'm gonna run out of time, but do outliers affect the z-score by much? Okay, so outliers do play a role in affecting the standard deviation, and so they could. Outliers will generally have a very high z-score of greater than 3 or minus 3 if it's an outlier in general. Adele, I'll have to come back to you with some better examples here. But I just want to keep going. In the interest of time, we're almost done. I might go a couple minutes over 12:50, and I apologize, but we'll I'll try to keep it there. Okay. You gave me a thumbs up, so thanks. Box plots. All right, so box plot is another numeric summary, or I'm sorry, another graphic display. And what it is it basically is a visual representation of the 5-number summary, okay? And so you are basically showing very little detail, right? So histograms, you get the shape, you get bimodal and skew and things like that. You lose a lot of that in the box plot, okay? But sometimes that's exactly what you want, right? If you want to make a whole bunch of comparisons between different groups, you want less detail. Your brain can't keep track of all the details. So you want less detail, but a quick summary, and box plots are great for that, okay? So you're gonna get a box drawn at Q1 and Q3, a line drawn inside the box at the median. You get whiskers that go to the min and the max unless they're outliers. There's a whole bunch of text on this slide. This is kind of the definitions. You get a left limit and a right limit, and I'm just kind of flying through all of this. I think the picture will be better, okay? And the picture will be better, okay? Oh yes, and Vanessa is our peer learning facilitator from AAP, and so feel free to reach out to her. And again, myself and the TAs, we're also here to help you as well. But I know it can feel a little intimidating talking to your professor. That I don't want you to feel that way, but I understand that feeling. So also feel free to reach out to us for help as well. Okay. So here is what a box plot might look like for our scores. So I created the, remember we created the scores of our test scores, and we looked at the summary where we have Q1 is 76 and Q3 is 92 and the median is 83.5, okay? So that's where the box goes, okay? Our box plot, Q1 is this line at 76, Q3 is this line at 92, and the median is this line at 83.5. So the 5-number summary gets put onto the box plot like this. You get the min at 65 and the max at 100. And this is what the box plot represents. So you got your 5-number summary gets represented with basically this line, this line, this line, this line, and this line. So that's your 5-number summary. If you have outliers, the box plot will represent the outliers with these circles, okay? And so what is this, okay? So you still have the min, Q1, median, Q3, and the max, but if there's outliers, there's something called a left limit and a right limit. And basically the way you find your right limit is you take the IQR. The IQR is the width of the box. It's the Q3 minus Q1. That's the width of the box. That's your IQR. And if you go 1.5 times the IQR above Q3, that takes you to the right limit. And if you go 1.5 times the IQR below Q1, that takes you to the left limit. And any observations beyond the right limit and beyond the left limit would be considered outliers, and they get dots here. So what did quantile type 5 equal do? Again, when we create the 5-number summary in R, there's technically a slightly different formula that it uses to find the quantiles, which is different from the method that I showed in the slides, okay? And the method I showed in the slides matches the method shown in the textbook, and so for consistency, I'm using that. But if you want the same results from R, you have to do quantile type equals 5, because there's technically different formulas for finding quartiles and stuff like that, and R takes into these accounts. Okay, IQR is just the box between Q2 and Q3, Q1 and Q3. IQR is the distance, is the length of the box or the width of the box. The width of the box is the IQR, because the box is represented by Q3 and Q1, and so its width is the IQR, and the right limit is found by going 1.5 times the IQR above, and the left limit is found by doing 1.5 times the IQR below. Okay, I apologize for going a few minutes over class today. That's all I've got for you. So we will end here, and we will see you guys next Monday. So have a good weekend. Don't forget to take the quiz, but again, review your notes, do some practice homework problems before you open up the quiz, because as soon as you open up the quiz, your timer begins, starts clicking away. And so you don't want to just like open it and then you'll get in trouble. So that's what we have. Can we see pics of your kids? I don't know, maybe. I'll have to think about that. All right, okay. We'll see you guys. Have a good weekend. See you Monday. I'll have office hours on Friday. Feel free to chime in, and we will we'll see you guys.